All right. So you remember our definition of calorimetry, correct? I like to break words down because if you know how a word is constructed, um, you can usually tell what it's all about. And this part refers to heat, and this part refers to measure. So calorimetry is basically just measuring heat transfers. And when you measure heat transfers, you've got to know several things. One is there has to be a temperature difference between the two objects in contact, even at the molecular level. So if in our examples last Tuesday, we had hot water and cold water. Put them together, they exchanged heat. Or you can drop a piece of metal and it's been sitting in boiling water, drop it in cold water, and there you have a transfer of heat due to a difference in temperature. But you also have to know how much of each substance you have. And the best way, I think, to determine the heat transfer that we represent with a small q is to look at the formula that we've been given for at least this method. So there's your difference in temperature between what the object started at and what it ended up at. This is the specific heat by mass, and this is the mass. So you have to know temperature change and you have to know mass. And depending on what you're solving for, if you're solving for how much heat is transferred, then you got to know this one too. You got to know specific heat. But if you're trying to solve for the specific heat, then you have to be able to determine the number of joules of heat that is transferred. And you know this one, you know that one, then you can solve for the specific heat. It's like any algebraic equation. If you've got several unknowns, you've got several variables, and you know all of them, the values for each of them except for one, you can solve for it. Okay, so let's get to the lab. Lab number 5. Let me see, where should we start? Let me start with the pre-lab questions. I think that's what they're there for, to kind of get you in the get your vehicle in gear, thinking in terms of heat transfer. So pre-lab questions, let's do that first. Pre-labs. Yeah. My brain's not working today. 1. Okay. 1 mole of acid and 1 mole of base react to form 1 mole of water. So if we represent these in generic terms, we would say 1 mole of acid plus 1 mole of base. And this designates acid, this designates the hydroxyl designates the base. Okay, and they're in an aqueous solution, obviously. And it produces 1 mole of water. Okay. We haven't talked about acid-base reactions yet, have we? Okay. So we have talked about types of reactions where you have double replacement, correct? Yeah. So if you look at this as a double replacement, then this cation goes with that anion to make water. Okay, that's what's happened there. Then this cation goes with that anion. It could be aqueous or it could precipitate. But what you have here in an acid-base reaction, you always get water. And this is the chemical definition of a salt. Now, it doesn't tell you that here, and it's not important for solving the problem, but I thought I'd throw that in for free. So 1 mole of this, 1 mole of that makes 1 mole of this. That's balanced. Okay, what's the question? Why is an excess amount of sulfuric acid used in part one? Oh, we haven't talked about the lab, so that's not going to make any sense. Right? We can do this, right? Let's reintroduce the concept of limiting reactant, right? If you have an absolute amount, you know an amount of that, and you know an amount of that, then what have I said? You're probably going to have one of them limiting. So in order to determine the limiting one, we have a procedure we go through. But in this case, what we want to do is be sure, absolutely certain, that the reaction has gone to completion. So we, as the experimenters, artificially increase one of them, right? We could have what we consider molar ratios of the two. Right? That's easy to do. But if we want to be sure the reaction goes to completion, we just make one of them excess. And then the limiting one is consumed completely, and there's some of the excess left behind, but we know the reaction goes all the way to the end. And let's be consistent here. We're using excess acid in our reaction, and this would be the limiting one. So the stoichiometry would be based upon this one, right? Even though we put an excess of acid in there with it, this determines the stoichiometry or the outcome, how much water is produced. Okay, so when we do that, we're going to measure an enthalpy for that reaction, right? Heat. And in this case, the pressure is constant. Right? So during the Tuesday's lecture, we learned that if the pressure is constant, then this is equal to that. They're both equal. That's the only condition we've seen so far where they are equal. We hold the pressure constant. And there's 1 atmosphere pressure on the whole thing, so we're pretty sure it's constant. Okay, so why then is an excess amount of sulfuric acid used in part one of the laboratory exercise? Well, so that we're absolutely certain that the reaction goes to completion. If it doesn't go to completion, then you can't say that it produced a certain amount of heat per mole of water generated. And that's what we're going to have here. We're going to have something, let's see. Yeah, question? No? Okay. Right. So if that makes sense to everybody, we'll move on to number 2. Now, of course, might as well while we're here. If our reaction, one of the steps in the procedures in here is going to use acid and base. I hope you've at least read through it. We're going to have a certain amount of acid, sulfuric acid, combined with a certain amount of sodium hydroxide base. Right? So if we balance this, and remember, in an acid-base reaction, you always get water. And what would be your salt? It would be the sodium and the sulfate. So sodium has a +1 charge, and sulfate is a polyatomic ion with a 2- charge. And so you need 2 of these, don't you? And this is cycle. Okay. So if we're going to balance that equation, we need 2 sodiums, correct? 2 sodiums. So that gives us 2 sodiums, 1 sulfate. That part's good. But now we've got 2 hydrogens and 2 hydroxyls. So 1 hydrogen and 1 hydroxyl, the other hydrogen and the other hydroxyl makes 2 waters. Okay. All right. So that's the balanced equation for the reaction that we're going to do for one of the steps, one of the procedures in our, let's see, part 1, actually, they tell us. Okay. So if we're going to determine the stoichiometry of this reaction, we know that for every 1 mole of this acid, it takes 2 moles of sodium hydroxide. Okay. So if we're going to use equal volumes of the two, that means we have to use twice as much sodium hydroxide because you need 2 times as much if they're at the same concentration. So if they were both 1 molar and we used 50 milliliters of this one, we need 100 milliliters of that. So what we do instead is to use 1 molar sodium hydroxide and a half molar sulfuric acid. That way, equal volumes will give you the ratio of 1 to 2. Okay. We'll talk about that in more detail when we get to the experiment. When we get back in here. Okay, that was 1. Let's look at number 2. And see if we can answer 2 without having to get into the procedure. All right. You're an engineer assigned to choose a material that will protect the spaceship from destructive heat when it re-enters the atmosphere. Okay. You're choosing between aluminum versus iron. And both of them, of course, will be solids on the heat shield. Okay. It doesn't say here, but we need to disregard the weight, right? Because aluminum is definitely less weight than iron, and it'd be cheaper to get into space. So we're only focusing on the heat capacity of the two. The molar heat capacity of aluminum, so this one, the molar heat capacity is 24.35 joules per mole degree C. And for iron, it's 25.10 joules per mole degree C. Okay. So which one should we choose for based upon its heat capacity? What we want to do is we want to choose one that will have a smaller rise in temperature for the same amount of heat. So one way to compare these is to say, all right, let's go back to our equation, right? The heat is equal to S and let's see, what should I say, moles? Is that right? Yeah, and change in temperature. So instead of mass, we're talking moles here because of the units of measure here. So if we solve for the S, then S is going to be equal to Q divided by N delta T. We can use either one of these. Actually, it just occurred to me that we can approach this as if Q is equal for both of them. Right? We want to dissipate the same amount of heat because as we re-enter the atmosphere, we're going to slow from a certain speed, 18,000 miles an hour, or maybe a little less, down to a couple of hundred before you pop the chutes. So we're going to expend the same amount of heat. So the difference between the two, actually we could set these up like that. That might be a better way to do it. This would be, say, iron. And they're equal to the same amount, so this would be aluminum. Well, for comparison's sake, we're going to say the same number of moles. The heat shields are the same number of moles of each. Right. So this is the same for both. And the change in temperature is where we're going to have a variation. This one is about 25, and this one's about 24, right? Okay, so if both of these expressions are going to be equal to the same value, okay, I didn't lose anybody yet, I hope. These two expressions, one for aluminum and one for iron, are going to dissipate the same amount of heat. or absorb the same amount of heat. Okay, so if the moles are constant, then we can ignore them, and we can say, all right, what happens since this one is getting smaller? If this gets smaller, then what has to happen to delta T for that to remain equal, for this to be a constant? If this gets bigger, that has to get smaller, doesn't it? So this is smaller than that one. Right? This would be, I don't know, an X value, and this would be, let's see, that would have to get bigger. This one would be greater than X. Right? So the change in temperature for aluminum would be much greater. Does everybody see that? Or is it too much math? We can, this was the math approach to it. We can approach it as in terms of intuition, if you'd like. Okay, so that proves it math, because if this one gets smaller, that one has to get bigger. So this is going to be smaller than, let's see, wait a minute. Yeah, we want a smaller change in temperature. So this one's going to be a bigger change in temperature than that one. This is the one we want because the temperature won't change as much. All right, so let's look at it this way. What does heat capacity mean? Heat capacity means for a change in, for a certain amount of heat absorbed by a material, if the specific heat capacity is high, then it will absorb more heat for the same change in temperature. If the heat capacity is low, then it has to change its temperature much more to absorb that same amount of heat. Okay, that means that the higher heat capacity is the preferred heat shield. Okay, let's take a pick. Okay, that was 2. Let's see, we have a 3. Yep, we got a 3. Okay. The enthalpy of solution of sodium hydroxide. What does that mean? The enthalpy of solution. What it means is, if you go from sodium hydroxide solid to sodium hydroxide aqueous, it's a certain value, an enthalpy here, of so many joules per mole of sodium hydroxide. Okay. Oh, they actually give it to us. Minus 44.5. 0.5 kilojoules per mole of sodium hydroxide. When it goes into solution, and that's a negative, yeah, it's exothermic. It's extremely exothermic. And that's typical of strong acids and strong bases, as a matter of fact. When you put a strong acid, say if I took a bottle of concentrated sulfuric acid at 98% by weight and tried to dissolve that into a liter of water, if I used enough of it, I could get it up so hot I couldn't pick it up. It wouldn't be a good idea. So that's why the rule of thumb, do as you oughta, add acid to water. Right? Add strong acids and strong bases to a lot of water, because with the heat capacity of water, the more volume of water will absorb that release of huge amounts of energy. If you do it the other way, if you put water in your strong acid, then with a little bit of water, it'll heat up so fast, it'll spatter, and it'll throw acid back up in your face. Okay, so let's get to the question here. With this information, if 10 grams of sodium hydroxide, 10 grams of sodium hydroxide were dissolved in 75 milliliters of water, 75 milliliters of water, okay, at 21 0.1 degrees C, what would be the maximum temperature attained? Right, so when it releases that energy, it's going to heat this mixture up. The heat capacity of the calorimeter is 1. So the big C, we call that the heat capacity of our calorimeter. Is 1 times 10 to the first power. That's just 10. 10 joules per degree C. Okay. So this is the one where we're going to use the formula that I gave you, right? What happens in Vegas stays in Vegas. What happens in the calorimeter stays in the calorimeter. So in this case, everything that happens in that calorimeter is equal to 0. So we're going to have a heat change or heat term that's due to the reaction that we can attribute to the reaction itself. There's going to be a heat change that's absorbed by the water, and there's a heat change that is either absorbed or the heat transfer involving the calorimeter. Okay? All right. So I didn't leave myself much room, did I? I'll put part of it up here then. So 0 equals, what's the Q of the reaction? Well, the Q of the reaction requires that we need to know, see, this is heat per mole of sodium hydroxide, right? We don't have moles yet. We need moles of sodium hydroxide. So let's go ahead and calculate that. How many moles of sodium hydroxide do we have? Well, we need the molar mass of sodium hydroxide. So we gotta look that up. And sodium is 23.00. So we got 23 for sodium, we got 16 for oxygen, and 1.01 for hydrogen. Just one of each. Right, 0, 6, 7, 10, 40. 3 plus 1 is 40. So that's 40.01 divided into 10. Is 0.250 moles of sodium hydroxide. Okay. So now we can introduce the Q for the reaction. The Q for the reaction is simply going to be, and we don't have to use the formula, that specific heat formula, because this is a reaction. All we need is dimensional analysis. We got this many moles, we got this much heat delivered per mole. We just multiply that one times this one, and the moles will cancel. So the heat of the reaction is that many moles of sodium hydroxide times the delta H, which is minus 44.5 kilojoules per mole. All right, let's make a change here, because these Qs are going to be using the joules. This is kilojoules. We'll save ourselves some trouble if we just go ahead and convert this to joules. So remember how we do that? What's a kilo? It's 1,000, isn't it? Joules. That's a simple way to do it. Just change the K into 10 to the third. Okay, so we got that term. Now, I'm gonna have to make room here. In fact, we'll erase that too. Be on the time, okay. So that's the Q of the reaction term. Now, how about the Q of the water? Well, the Q of the water is going to be our SM delta T. Right? So what's the S for water? We have to look it up. Right? 4.184, I think, isn't it? I believe it is. Memory serves. It should be in useful information. That's joules per gram degree C. So how many grams of water do we have? Well, for our purposes, the specific gravity of water is 1 gram per milliliter. Somebody go away and come back. Let me see. Oh, there's Kathy. Now we're all together. So for this, we're going to equate this to 75 grams. So 75 grams goes over here. And the grams here cancel the grams there. Now we need a term for the temperature. Change in temperature. Remember, delta T equals final minus initial. So what's the final temperature? That's the question, right? That's the question. It's unknown. Minus the initial temperature, which is 21.1 degrees C. Okay. Now we got one last term, Q for the calorimeter. Right. For the calorimeter, you can equate this. If we say Q equals SM delta T, for the calorimeter, we take the masses and the this part right here, both of these together, and just mash them together because the calorimeter has got several different components, right? We can't parse them out into individual. So we just do the calculation. We determine the calorimeter constant for our calorimeter, and there's a procedure in here that we'll go over in a minute for doing that. And this becomes C. So our formula is Q equals C delta T. That calorimeter constant is in, notice mass is missing. Mass has already been incorporated into it. So it's only joules per degree C. So for this term, what we've got is C, which is 10 joules per degree C, times a change in temperature, which is the same as the water. Because these procedures, usually what you do is you put one of the components in the calorimeter and let it come to equilibrium with the calorimeter. So when you measure the temperature of, in this case, water in your calorimeter, it's going to be the same temperature as the calorimeter. So its initial temperature of the calorimeter is exactly the same as the water. Okay. So all we have to do now is solve for the unknown final temperature. Okay. I'm going to erase these things so I have room to scribble. All right. So now we just have to reduce this to its simplest form. All right. So we have this one times that one will be the Q for the reaction. And it's in my hand. 0.25 times 44.5 exponent 3. Change the sign. 44.5. Change the sign. And the there we go. Times this one times that one. And I get minus 1.11 times 10 to the 4th. And moles cancel, leaves us with joules. So there's the Q reaction term. Okay. Next, we add the water term. In this case, we're going to have to divvy it out. We're going to have 4.184 times 75. And that is, I'm going to put it in standard notation. No, well, I better I'm using scientific, I better keep that. 3.138 times 10 squared. And the grams cancel, so that leaves us with joules per degree C. If we multiply that times TF, then here's the TF term. TF. Okay? And now, this one is a negative. So we're actually going to subtract this term right here, right? This term right here times that one, right? We did it here to get that value times this one, and then this one now is times 21.1, which is 6.621 times 10 to the third. And that grams is already canceled out. Now degrees is canceled out, and this is joules. Okay. Now we need the calorimeter term. The calorimeter term is going to be distributed out in this and that. So we're going to have this term 10 joules per degree C times TF. Right? And then we're going to subtract, because this is a negative, 10 times that. So what would that be? 2, 1, 1. And the degrees cancel. So this is left us with joules. Okay? I'm keeping all the detail for this one calculation so that I don't lose anybody. Okay. Now what we have to do is gather all the numbers together and the expressions with the unknowns together separately. So what we've got here is this minus, let's see, here it is. We're going to change this. Twist that. Go ahead. Yeah, this one minus that one. So these are two minuses. Right. And we have this one, another minus, 211. So this one, and this one together give us minus, I'm going to write these in standard notation this time. 1795.7. Yeah. And this is joules. Okay. Then we can add this one with this one. Okay. So that's let's see, 10 squared would be 313.8 and 10 plus. So this one is 323.8 TF. And the units here are joules per degree C. Okay, so what we want to do now is get this one on one side and this one on the other. So if we take this one over on the other side, the negative goes away. I just change the sign. So we've got 17,957 on this side equals 323.8 TF, and TF then is equal to 17,957 divided by 323.8. Let's see. Yep, it's in my calculator. I just check to be sure it's the correct one. And this is 55. Let's see. We're limited. Now that's we can treat this as an exact value. So we're limited to 3 significant figures. 55.5. 3C. So when that reaction takes place, from 10 grams, right? Is it 10 grams of sodium hydroxide? Yeah. In 75 milliliters of water, the temperature went from, it was doubled. Degrees Celsius, it was doubled. 21 to 55. Ready? I got it worked out here in my key, and it's a little bit different than that. But that's okay. Rounding error. Okay, is everybody clear on how to do these calculations? Because this is the format for how we're going to do our calculations in the when we run our experiments. What we're going to do is we're going to measure the before and after temperatures, the initial and final temperatures here and here. And then this one is going to be unknown. Q for the reaction is unknown. Okay, so we'll solve for that one. These will be known and known because we're going to determine them in the lab. Okay. All right. Let's see, that was 3. Do we have any more, or is it just 3 of them? Okay, so we can look at the lab now. Try to make sense of that procedure. All right, first thing we have to do, the procedure starts on the 3rd page, I think. Yeah. The enthalpy of neutralization is the acid plus base. Do that one first. Then we're going to do 2 procedures of heats of solution. First one is sodium carbonate, which is sodium carbonate, that in water. And the second one is sodium bicarbonate. Right? We'll put that in water, measure the temperature change, and calculate its heat of solution, its enthalpy of solution. For both of them. The first one, of course, is going to be the enthalpy of neutralization. All right, but before we can do that, we've got to build our calorimeter, and we have to determine the calorimeter constant. Right? How much heat is that calorimeter either going to bleed into our reaction? If it's endothermic and the temperature starts to drop, it's going to take some heat from the calorimeter. If it's exothermic, then the calorimeter is going to absorb some of that heat and bias our results. So we need to account for the calorimeter and its the part it plays in the chemistry of each one. So that's what this page right here is about. This one that says determine a calorimeter constant. The first rule is once you get this calorimeter built, do not change any of its components. Leave the thermometer there, leave the lid there, leave the 2 styrofoam cups intact. Right? Don't change anything. Right? Otherwise, you've got to start all over again and determine a new calorimeter constant. So we're going to need 2 thermometers because one has to stay with the calorimeter and the other one is with whatever else you're going to add in there. That's only for the neutralization experiment. You'll have to be sure that the temperature of the acid and the base before you put them together are the same. Okay, so how do we do the calorimeter constant? We're going to take that example from the lecture where we added hot water and cold water together, and that's the way we're going to do it. So in this case, we're using 75 milliliters of room temperature water and 75 milliliters of hot water. We're going to boil the water, but by the time we start to put them together, the temperature is going to drop from, I don't know, 98 or 97 at this altitude down to probably in the neighborhood of 60. But that's good because the room temperature water is going to be around 22 or 3, and then the hot water is going to be 60 or 70. So that's a good temperature differential to get a reasonable estimate of the calorimeter constant. Okay, so so for the calorimeter constant, and we saw an example of our calorimeter in the lecture, right? We just have two styrofoam cups, one inside the other, and we have a lid, and we have a hole in it, and through that is our thermometer. Okay, should go up a little further than that, and we're going to use the thermometer to stir things around. We just have to be a little careful. Okay, so that's our calorimeter. In order to determine the calorimeter constant, we're going to be depending upon this reaction. 0 equals Q of the hot water plus the Q of the cold water, room temperature water, I say hot and cold, and then the Q of the calorimeter. Okay, so when we parse these out, the Q of the hot water is going to be S for water, 4.184, times the mass of the water. In this case, it's going to be 75 grams. Okay, 75 milliliters. We're going to assume that the water is specific gravity of 1 gram per mil. So if we have 75 milliliters, we got 75 grams. And then our change in temperature is going to be final minus initial. Okay, so that's going to be the hot one. The cold one is going to be similarly constructed, H2O. This mass is going to be the same volume, therefore the same mass of water. It's going to be hot. And what we're going to have is distilled water on the hot plate, and it's going to be boiling. So you just pour some into a graduated cylinder, 75 milliliters, and that's how you measure it. And then this one is also times final temperature minus initial temperature. Okay. Now, when we put them together and they come to equilibrium, what's the final temperature? Well, we don't know yet. We have to measure it. Okay. But it's going to be exactly the same for both of them, because now they're together, and the temperature of both hot and cold water together they sort of met in the middle. Okay, so this is going to be the same temperature for both of them. Initial temperature will be different. This will be whatever. This is I didn't subscript. Hot, cold. This one's going to be room temperature initial, like 22 or 23 degrees. And this is going to be hot water temperature, 60, 70, 80, some maybe. You have to measure that too. And then we have the Q for the calorimeter. It's just going to be the calorimeter constant times change in temperature. The final temperature minus the initial temperature. All right. The way we set this experiment up, the initial temperature of the calorimeter is going to be the same as the cold, because we're going to put the room temperature water in the calorimeter first, and they'll come to equilibrium. So these two temperatures will be the same, and these will be the same for every one of them. Okay, so we're going to measure those temperatures. We're going to know how the mass of the water that goes in. We're going to know the specific heat of the water. The only unknown in this whole equation is this one right here, the calorimeter constant. Once you've got that data, you can solve for the calorimeter constant. And then we're going to use that in subsequent experiments, 1, 2, and 3. All right. So a word of advice. When you're setting this experiment up, you've got your hot plate here, boiling water. There's bubbles coming up here. Boiling water. And then you got to measure it. The one rule that you want to keep in the back of your mind is that you want to know the temperature immediately before they're combined. So you have, well, one of your partners is watching the water inside the calorimeter to get its temperature. And the other one, you take this water, right, put it into a graduated cylinder up to 75 milliliters. And once you get 75 milliliters, you can stick the thermometer in there, right, and let it come to that temperature. But you want the temperature immediately before you combine them. You don't want to take the temperature and let it sit because it's going to drop. So you want the temperature right before it goes in the calorimeter. Okay. All right. So that's the procedure for calorimeter constant. Let's see. Let's see, these are going to be 2 different cues here. For the rest of them, you're going to have the cue for the reaction as an unknown. And this one's going to be the cue for water. Okay. All right. So for the first one, the enthalpy of neutralization. Okay. You're going to have the controlling reaction here. The neutralization reaction itself is the one I put up earlier. So you have sulfuric acid in this aqueous, and you have sodium hydroxide, aqueous, and yields water, liquid, plus sodium sulfate, aqueous. Okay, and we needed 2 here and 2 here. All right. So the procedure calls for 0.5 molar sulfuric acid, 0.5 molar. And for sodium hydroxide is 1 molar. There it is, 1 molar. Okay. You're going to transfer, well, however you do it, you're going to end up with 60 milliliters of this. And you're actually going to use only 50 milliliters of this. I know the procedure says put 60 milliliters of sodium hydroxide solution in a beaker, but eventually you're going to measure out 50 milliliters of sodium hydroxide. So now that's why I mentioned earlier, this is in excess, this is limiting. So our reaction stoichiometry is limited by that right there. Okay. All right. Let's see. So I'm checking myself. The sulfuric acid, this one goes into the calorimeter. We put this one in here first. and then measure its temperature. And then you have 50 milliliters of this, and you can just leave it in the graduated cylinder with your thermometer. Yeah, 50 milliliters here, 60 milliliters there, and you watch the temperatures until they're equal. Okay. Now, I have in the past had students that we didn't have enough time to let them equilibrate, so we had to use them at two different temperatures. There's a modification to the equation that I can give you where you can do that, but it's a lot easier if they're both the same temperature to start with. So initial temperature of this would be initial temperature of the water, because we're going to make water. So the initial temperature of both of them together, what's the volume? The volume is 110 milliliters, right? Or 110 grams. We have to assume that when we add these together and the reaction occurs, 110 milliliters is the volume. And we don't get a change in volume due to the reaction. Now it's going to get hotter, right? So that's going to increase the volume. But based on what we've got here, this is also 110 grams. And that's not going to change. That's what we're counting on. Okay, so we've got this, and Q of the calorimeter. So when we run our experiment, we've got the Q of the reaction is our unknown. What's the Q of the water? Well, this is where it's important that the temperatures be the same. Because if they are, then we can combine all of this together in that term. Right? We have the specific heat of the water. We've got the mass of the water, which is 110 grams. And we've got the change in temperature, final minus initial. Right? The initial temperature, as long as it's the same for both of them, we can plug it in right there. And then after the reaction is complete, and the one thermometer that's in here, you watch the temperature. And the temperature is going to go up like that, and then it's going to start down like that. So you get the peak temperature. That's the final. So we got that, this, and this. That term is calculated. Then we also have the Q of the calorimeter. We have the C value that we calculated before. And then we have the final and initial temperature, which is going to be exactly the same as these two. Right, so we know all those terms. This is the one, Q of the reaction. And this is going to be in joules, just joules, Q of the reaction. So this Q is an extrinsic property. It will vary depending on how much of this stuff you put together. So we've got to ratio it to something so that it becomes an intrinsic property. So we ratio it to, let's see, X amount of joules. We ratio it to the number of moles of water produced. Okay. And since this is the limiting one, we don't have to calculate from that. We just need the balanced equation. Okay. 50 milliliters times 1 molar is 50 millimoles, correct? So 50 millimoles of sodium hydroxide, 2 to 2, that means 50 millimoles of water. So we do need to convert that to moles. So 50 millimoles is 0.050 moles. Right? Move the decimal 3 places to the left. So now we have this value, we divide that into it, and that makes it an intrinsic property then. Right? It's ratio to the amount of water produced. So this value, whatever it happens to be, can be compared to the accepted value, which is on, let's see, your last page, I think. Yeah, in this table right here. This table lists the bottom one shows you hydrogen ions plus hydroxyls yield water. That's an acid-base reaction. And the value, the accepted value is minus 57.9 kilojoules per mole. So to compare it, right, this is joules, you're gonna have to divide by 1,000 to get kilojoules. Okay, once you've got that value, then you can compare it to this one and see how close you are. Okay. All right, I got 13 minutes to go. I can do, this was the number one procedure. I spent a lot of time on that one. The number 2 and 3 procedures are exactly alike in the way we perform them. They're heats of solution. I'll give you a hint. One of them is going to be exothermic and the other one's going to be endothermic. One of them is going to get hot. Temperature is going to go up. The other one's temperature is going to go down. Okay, so let's look at them 2 and 3 together. When you write your report, actually when you put the information into your lab notebook, in your comparisons of your results, compare them to these values. Right? It's got 4 values. The top one you don't need. That's sodium chloride dissolved in water. There's sodium carbonate dissolved in water, has a delta H, and that gives it away right there. you can tell by the sign which one's endothermic and which one's exothermic. And sodium hydroxide, sodium hydrogen carbonate is the one just above water, the acid-base reaction. Okay, so for 2 and 3, we're going to have some salt. It's either going to be sodium carbonate or sodium hydrogen carbonate, often called bicarbonate. This is Arm and Hammer. Arm and Hammer sodium bicarbonate. That's all it is. Okay, so we're going to have the same setup here. We're going to have a Q for the reaction is our unknown. Then we're going to have a Q for the water. Right? You have a certain amount of water that's in your calorimeter. And then you have the Q for the calorimeter. And you set these up exactly the way that we did before. Except this time, you know how much water is in there to start with. We're not making water like we did with acid base. The water's in there. And you check that temperature as your initial temperature for both these two. And then the final temperature is whatever you measure it. Then you need to know the mass of this one. And the report is in kilojoules per mole. So whatever mass you have for this one, you need to calculate the moles. You need moles. You need moles. Because you're going to get an extrinsic value here, just like before, that varies with the amount of this compound plus the amount of water. So we want to intrinsify it. We need to change it to an intrinsic value. So what you do is you take the moles here and divide it into the Q that you get there. Okay. And then, of course, it's in kilojoules, so you'll have to be sure that you've got your right units. Right. Once you find the Q for this reaction, then you convert it here, and that's what you compare with these values. Okay? So you need to set up your lab notebook the way you have in the past, right? So that you're ready to receive the data, and you know the data that you're going to collect. Right? You're going to have temperatures, you're going to have masses. So it's best if in the data section you have it set up in, you can just do it in a list, right? For experiment 1, you need this, experiment 2, you need this with a blank. And the units measured, right? So it'll be easy to find where you need to plug that information in. And then your calculations, of course, will come later. Let's see, are there some post-lab questions? There are laboratory questions, right? Actually, the laboratory questions reference calculating the enthalpy of reaction for each one. Oh, and then a fourth. Yeah, a fourth and a fifth one. Okay. Take a look at those. We won't talk about them right now. So once you get, once you've had a chance to look at the procedure and put it in your notebook and take a look at those post-lab questions and see, they're probably going to scratch your head and say, how do I solve that? And then we'll talk about it.